we present recovery of continuous 3D refractive index map from discrete intensity-only measurements using neural fields, or DeCAF. In this work, we consider a specific microscopy modality named intensity diffraction tomography, or IDT. IDT is a non-invasive, label-free tomographic imaging technique. It is a novel variant of the classic optical diffraction tomography and can be useful for physiology, oncology, and other biomedical applications. The left figure shows a general structure of the IDT setup. It contains a programmable light source, sample holder, an objective, tube lens, and a digital camera. The figures on the right displays different real IDT configurations. Compared with the traditional ODT technique, IDT only measures the intensity of the scattered light, meaning that the phase information is lost during acquisition. On the one hand, this significantly reduces the cost and complexity of equipment by removing the interferometric devices. On the other hand, due to loss of phase, the reconstruction of IDT becomes much harder than ODT because it's nonlinear and cannot be characterized by classic linear Fourier diffraction theorem. A full IDT acquisition usually contains measurements responding to zero illumination of the sample from different angles. By programming the light source, we can have different illumination patterns. Common patterns include dense, annular, and multiplexed. Additionally, by illuminating the sample from different angles, the geometric information of the sample are stored in image measurements. Overall, the goal of IDT reconstruction is to recover the 3D refractive index of the sample from 2D intensity-only measurements. Here, the refractive index defines the optical property of the sample. It is a complex number where the real part of Ri characterizes the phase and the imaginary part characterizes the absorption. By recovering the distribution of the sample's Ri, we demonstrate the morphological structure of desired sample in 3D images. We adopt neural field to address this reconstruction problem. It uses deep neural network to represent a physical field rather than using the discrete vectors. Different from common convolutional neural networks, the input of MLP is the 3D spatial coordinates in the sample space, and the output is refractive index value at that location. This means that the network learns a neural representation of the sample by being trained to map the coordinates to Ri values, which means the MLP itself is the desired 3D reconstruction of the sample. To retrieve the 3D model from the network, all we need to do is to query the coordinate grid. Additionally, we can conduct pixel super-resolution for this 3D model by querying a denser coordinate grid. The second feature of DeCAF is it fused light propagation model to ensure measurement consistency. Here shows the principle of physical model we use in the experiments. The sample scattered light field can be approximated by the sum of light fields generated by each axial slice. Note that DeCAF is not restricted to specific light propagation model. It is compatible with other physical models as long as the model is differentiable. By integrating the physical model into the loss function, DeCAF can directly compute the mismatch between predicted Ri volume and the measurements. This means no ground truth image is required for supervision. The feature significantly expands the application of DeCAF to imaging regimes where the training data is hard to acquire. The third feature of DeCAF is a proposal of a new coordinate encoding strategy. Currently, the most popular encoding strategy is positional encoding. which performs a 1D Fourier series type expansion for each axis. However, this expansion does not work well for representing rotated features. We propose radial encoding to address this. The idea of radial encoding is very straightforward. Consider the coordinate xy. Rotate the base axis to get new coordinates. Then, expand the new coordinates similar to positional encoding. Experimental result shows radial encoding recovers more detailed reconstructions. The fourth feature is that DeCAF integrates external regularization to synergistically improve image quality. The encoding and MLP network work together to impose a strong internal regularization to thin sample reconstructions. In this algae example, our result using just internal regularization shows much clearer reconstruction than traditional Tikhonov reconstruction. However, internal regularization failed to reconstruct thick samples. We designed two external regularization terms. The first one is a 2D noise reduction term that removes noise in axial plane. This is inspired by success of denoising priors. Note that the deep denoising prior used here is trained on natural images while performed on IDT samples. The second one is 1D axial continuity that ensures neighboring axial slices are similar to each other. These two regularizers jointly formulate a 3D regularization on the sample. Next, we show quantitative result on simulated samples. Our method reconstructs the sample with significantly less artifacts and show better sectioning effects. Quantitatively, our method also shows higher SNR and lower mean squared error than previous works. We also validate our method on experimental data. This is a 3D sample of datum algae. As we go through the sample slice by slice, we can see mesenchymal artifacts from traditional methods on the right, while our method on the left shows clearer axial sectioning effect. This difference is also obvious in the lateral view. As our model continues to represent the sample, we also produce smoother results than the traditional method. This is another example of human buccal epithelial cells. We see similar improvement in our method with less artifacts, image quality improvement, and great sectioning effect. Here, we demonstrate again of our ability to synthesize views of samples on demand. Finally, we show a result from C. elegans sample. Our sample is smoother and much clearer than the Tikhonov reconstruction. Here, we show the improvement on the lateral view. Thank you for your attention.